Okay, let's look at some Euler's method. I'm going to teach you how Euler's method is used, and if you want to print the guided notes sheet that I give my students, you can go to this bit.ly link. It's bit.ly/not Euler, because everybody wants to call it Euler's method when they first see that, but it's actually pronounced Euler, and that is case sensitive. So let's talk about Euler's method. And it is a technique that we will use in the world of differential equations, where we can approximate the values of the solution to a differential equation when you are given some initial condition to the differential equation, and also some step size, which we will call delta x. And so at this point, I assume you know what a solution to a differential equation is, maybe not necessarily how to find the solution. And with Euler's method, we will not be finding the explicit solution to the differential equation. However, we can use the differential equation and a little bit of other information to estimate values of the solution. And what I'm going to do first is show you kind of graphically the brains behind Euler's method. And so right here we have a differential equation. It's x plus y, dy dx is x plus y. We have our initial condition. So there's your initial condition. I'll just abbreviate that IC. We have our delta x. That is our step size. And some textbooks will call that an h instead of a delta x. So if you see h in the context of Euler's method, it could refer to the delta x. And we are starting with this initial condition for our solution. Now, the only thing we know right now is that my solution to the differential equation will pass through the point -1, 1. So I can plot a point at -1, 1 and show, and I know that my curve will go through that point. Now, what I can also find out about my curve at the point -1, 1, because I have the differential equation, well, that's like the derivative. I can find the slope of the solution as it goes through that point, and that slope is found by adding the x and the y, and so -1 plus 1 is 0. And so I am trying to get all the way over here to x equals 1. So here's my objective. I want to go from -1 all the way to 1, and we're going to go by step sizes of 1. So it's going to be a two-step Euler's method. And what we'll do is we will use that given slope, and what we'll do is we'll assume that the solution will carry that exact same slope for the entire first interval, and after I go one step size of 1. So there's my delta x of 1. So I went one step size. I have now arrived at the point 0, 1. And so what I can do now, I've arrived at my next point. I can now recalculate the slope of the solution. We have moved. My slope is now going to change to 0 plus 1, which is 1. And then I will again carry out that slope for the next delta x of 1, which will take me with a slope of 1. That will carry me all the way to the point right here. And I'm now at the point 1, 2. I wanted f of 1, and so what I can say now is that with this two-step Euler's method approximation, f of 1 would be approximately 2. And so there is the way Euler's method works. Now, if you want the Euler's method approximation to be more accurate, then don't take such a large step size. Maybe instead of going from -1, 1 all the way to x equals 0, maybe we carry that 0 slope only half a unit and then recalculate the slope when I get to -0.5. And the more calculations you do and the shorter your step size, the more accurate the approximation will be. But this is my way of showing kind of graphically how Euler's method works. Now, that said, we usually will not do Euler's method with a graph like that. There are two prevailing ways to do Euler's method. One is through a recursive, iterative, I call it like a memorized formula approach. I choose to organize mine with a table. So if you don't want to learn the table method, then just go ahead and stop watching this and go find somebody that does the formulas. I think the table is a better way to organize. It just works better for me. So that's what I'm going to use. So when we're dealing with Euler's method, you'll always be given some differential equation or some representation of the derivative. You'll have the initial condition, and they will also give you the delta x, or they'll provide enough information for you to figure the delta x, kind of like you figured delta x's with Riemann sums in a previous unit. The challenge, though, is going to be to figure out how much y changes. So if we look at this situation right here, we have the differential equation. I know my initial condition. So there's my initial condition, 0, 1. So I'm starting at 0, 1. My x's are increasing by 0.5. And so I already can fill out my column for my x's. If my x's increase by 0.5, I'll have 0, I'll have 0.5, then 0.5 plus 1 is 1, then 1.5, and then eventually I get to 2, which is where I want to end. So we're going to stop at 2. What I don't know is how much my y's will increase. If I can find out how much my y's increase, then I can just add that change in y down this column until I get to some y value that goes with the x value of 2. And so to find the change in y, what we're going to do is take our differential equation, which is dy dx equals 2x plus y, and we will separate the dy from the dx by multiplying both sides of this equation by dx. And so we have now dy is equal to 2x plus y times dx. And if you can think back to algebra and slope and how that's connected to calculus, in algebra, we found slope by calculating a measurable change in y over a measurable change in x. In calculus, when we do slopes, it's usually at a single point, so you cannot measure a change in y. The distance between the y's gets infinitely small, and we represent that infinitely small change by replacing the delta with a d. So this dy equals 2x plus y dx can be thought of as a change in y is 2x plus y times a change in x, which is going to be my next column on my table. So we have a formula for our delta y, and we already know that delta x is 0.5, so I can replace that delta x with a 0.5. And then to figure out what my change in y is, I'll simply use this formula. So for this first row, my change in y is going to be 2 times 0, that's 2 times the x, plus my y, which is 1, times 0.5. And so 2 times 0 plus 1 times 0.5 is 0.5, which means my new y is going to be my previous y1 plus that delta y of 0.5, and it's going to end up being 1.5. Now what I like to do is I like to have one more column in my table, because if this shows up in free response on the AP exam, they really like your tables to be very clear. They need to be clearly labeled, and it needs to be easy for anyone to read and see what you're doing. So what I like to do is I like to have one last column here, and to get my next y, my new y coordinate is my old y coordinate, which was 1, plus my newly found delta y, 0.5, which is 1.5. And now I have an x and a y coordinate, I already knew my x coordinate was 0.5. Now I have a y of 1.5 to go with that, and I can now rinse and repeat. I can recalculate my change in y using my formula. It's 2 times x plus y times plus y, my y is 1.5, times 0.5, and we will figure that. And once we figure that change in y, we'll add that to 1.5. That'll give me a y coordinate to go with my x of 1. And then I'll repeat. And what I'm going to show you here is how we can use, if it's a calculator active problem, which these typically aren't, but I'm going to show you how to use calculator anyway. If it's a calculator active problem, I'm going to show you how on the TI Inspire you can do this rather quickly. And it's a cute little technique that you can store a function into your calculator. However, this function is a function of x's and y's. And so while I typically would say, okay, let's let f of x equal, and we do control colon equal right here, and I can type in anything to store something for f of x, but this is a function of x and y. So we do that by saying f of x comma y. And now I can actually have a function of two variables. And I am going to do one thing different. I'm not going to use f while I could use f. I might get confused because f of x is used to reference the solution to the differential equation. I'm going to call this dy for delta y. So dy of xy is, and then I'll simply put in the equation for delta y, which is 2x plus y times 0.5. So 2x plus y times 0.5. Hit enter. It is done. And now I need to compute my delta y when x is 0.5 and y is 1.5. So now I'll go back to my calculator. dy when x is 0.5, comma, y is 1.5. Hit enter. And there is my delta y of 1.25. So now I can go back to my table here. This is 1.25. And to get my new y coordinate, I will take my previous y coordinate, 1.5. I will add the newly found delta y, 1.25, and that's fairly convenient. That's going to be 2.75. So now I have my new y, 2.75. And then I can recalculate my delta y. So I'm going to go back to my calculator, and my delta y is going to be my function at 1, 2.75. So my delta y when at the point 1, 2.75. Hit enter, and I get 2.375. So I have a new delta y. So I'm going to calculate my new y coordinate when x is 1.5. That's my previous y, 2.75, plus that delta y, 2.375. And now it's getting a little bit ugly. I could obviously do that without a calculator, but why hurt yourself? I need to add that delta y to 2.75. So we're going to take that 2.375, add that to 2.75, and I have my new y of 5.125. Need to recalculate my delta y, so back to my calculator. My x is 1.5, and my y is 5.125, so my delta y at 1.5, 5.125, I get 4.0625. And then finally, last step, I need to add that delta y to the previous y. And I am going to get, so I take that, I need to add that to the previous y, which I can see in my last two entries there. So that previous answer plus 5.125. And I'm getting a new y of 9.1875. 9.1875. And right there, I have filled in the y value to go with the x value of 2, which is what I wanted. So now I can say that f of 2 is approximately 9.1875. And so there is an Euler's method approximation, and I forgot to uncover this up here. I mentioned it. Our challenge with Euler's method is to compute the change in y. So we go through all of those calculations, all that iterative process to figure out what the delta y is. We add that to the previous y, and then it's just a little bit time consuming. The good news is if you see this on the AP exam, it's typically not a very long one. It's typically just like a 2-step process, maybe 3 steps. You usually won't see a 4-step process on the AP exam. Okay, so let's look at the next one. Very similar situation. We have a given differential equation. We have our initial condition, f of 0 is 1. This one, however, is a tiny bit different because I tell you where we're ending. We're going from 0 to 1.5, only I didn't give you the delta x. I told you how many steps to use. And so we'll compute our delta x the exact same way we figured delta x with Riemann sums. It's b, we're finishing at 1.5, minus a, we're starting at x equals 0, divide by the number of steps, and we get a delta x of 0.5 again. And so if my x's are increasing by 0.5, I'll go from 0 to 0.5 to 1.5 to 2. Wait a minute. Okay, that's not right. 0.5 plus 1, 0.5 plus 0.5 is 1. Then I'll end at 1.5. There we go. So we finish at 1.5, and again, we're trying to compute our delta y. And this time, I'm going to show you how to do this with Desmos, because starting in 2025, you can actually use Desmos on the AP exam. And so let's go to Desmos real quick, and I'll show you how to do the exact same thing in Desmos. And I believe Desmos is actually a good bit more efficient than the TI Inspires. So hopefully the Desmos that's embedded on the AP exam is just as fluid and easy to use as the one that's on their website. And so we will again define our function as xy. So I'm again going to use dy of, let's see if this works, x comma y. And I need to set that function equal to x squared plus y, and my delta x is going to be 0.5. And so let's see if this works. Okay, and I just paused the recording for a second just to see if Desmos would understand the dy notation the same way the Inspires does, and it does not. So we cannot use dy this time. I think I'm just going to call it d of xy, and I just tested with a bogus x plus y. So I need to change my differential equation. It's x squared plus y times 0.5. And I just use my keyboard, parentheses, x, and you hit the caret above the 6, shift 6, x squared, tab out, plus y. And then I need to multiply that by 0.5. Done. I need to clear this one out. And we need to compute our slope at 0, 1. So I'm going to go back to Desmos here, and I'm going to do d of 0, comma 1. And as soon as I hit the 1, it will tell me what my change in y is at the point 0, 1, and that is 0.5. Do that in blue. And so I will now find my new y, 1 plus 0.5, which is 1.5. And so there's my new y, 1.5. And we will rinse and repeat. And I know that calculation 1 plus 0.5 is really mundane, and everybody can do that in their head, hopefully. But I still like to include that in my table because I don't want to risk losing points if this were a free response situation. I want everything I'm doing, every calculation I'm using to be visible to the AP reader so that I don't risk them wondering, oh, how did we magically go from 1 to 1.5? We don't want them to have to assume we're adding them. I want to have that explicitly in the table just to be safe. And I don't know if it's 100% necessary. I've never read an Euler's method problem myself, but I just want to be safe. And for the sake of time, I'm going to pause the recording, and when you look up at this again in a minute, you will see the final solution. Okay, and so I ended up with a solution of f of 1.5 is approximately 4.0625. A point of emphasis, be sure that if you are doing any approximation technique, just to keep the gods of math happy, this could be Riemann sums, it could be Euler's method, it could be linear approximation. We're going to get into approximation techniques later in the year with sequences and series. Make sure that you indicate approximation by using the approximate symbol. Don't say equals, because this is indeed an approximation. And if you want to see my calculations in Desmos, here they are right here. And so you can see it. I just very slowly or quickly, I guess, punched them in, and you can see all of the different calculations there. And then there's one more that I want to look at. And this one I'm not going to use a calculator because, as I mentioned earlier, these are typically non-calculator questions on the AP exam. So let's look at one without a calculator. Here we have a table of values. We don't have like an explicit differential equation that is a function of x's and y's. We just have a table of values. We do have the differential equation up here. I said, or we don't have an explicit differential equation. We kind of have one here, but I still don't know what the function f or f prime is. I do know my initial condition is 2, 3, so I'll start there. We are going to 2.4 from 2 with 2 steps of equal size. So the delta x, 2.4 minus 2 divided by 2 is going to be 0.2. So now I can increase my x's by 0.2 until I get to 2.4, which is a whopping 2-step process. And now we need to figure out what the delta y would be. And this one's not going to be as tough to figure out because I gave you dy dx is f prime of x. And if you multiply both sides by the dx, you get your delta y is f prime of x delta x. And so we have that for our delta y, which is correct. However, a lot of times on these problems where they give you a table like this, they don't give you the dy dx equals f prime of x. They'll simply say, let f of x be a solution to a differential equation. Values of f prime of x are given in the table below. They won't explicitly say dy dx is f prime of x, but you could generate that equation itself because that's essentially saying y prime equals y prime. Dy dx and f prime of x are 2 different notations for the same thing. And so we are going to now compute our delta y's starting with 2, 3, and delta y is f prime of x. That's going to be f prime. That's not what I wanted to do. Undo. There we go. That's going to be f prime of 2 times delta x, which delta x is 0.2. So I'll replace my delta x with the 0.2. F prime of 2 is negative 0.5. So negative 0.5 times 0.2 is going to be negative 0.1, which means my new y is going to be 3 minus 0.1, which is 2.9. And now we just have to do this one more time. So my new delta x, or my new delta y is going to be f prime of 2.2 times my delta x, which is 0.2. F prime of 2.2 is negative 0.3 times 0.2. And that's going to be negative 0.06. Yeah. and then 2.9 minus 0.06. You can actually leave your answer like that if you want to. However, these do show up in multiple choice sum, so I'm going to go ahead and clean that up. 2.9 minus 0.06 is going to be 2.84, and that's going to be my approximation. And so f of 2.4 is going to be approximately 2.84. But again, if this is free response, I would leave my answer as 2.9 minus 0.06 just to eliminate the potential of careless arithmetic errors. And there is Euler's method, a few examples. Hopefully that makes some sense to you.